deal with so-called So regularity structures deal with so-called singular stochastic PDEs. So this is what we want to look at, singular stochastic PDEs. Yeah, so what is a single stochastic PDE? Maybe the best is really to start with an example. And there's a very famous example. It's maybe one of the first examples really studied by this theory and by similar theories. It's a so-called Kpz equation, where Kpz stands for three physicists, Carter, Pdes, and sum. And so what is the idea of this equation? So this equation is supposed to model interface growth. Yeah? So it's an equation to describe interface growth, to describe stochastic interface growth. Stochastic interface growth. So let's see what this actually means. So one famous example is, so I, for instance, take this sheet of paper here, I put it on fire, and what will then happen is that the fire will really eat the paper. And what you're interested in is in the interface between air and paper. So like burning paper, And so the interface, how does it look like? I mean, it probably looks something like this. I don't know, maybe something like this. Probably what I drew here is still way too rough. And so if you're imagining that this fire is now eating the paper, the growth really goes upwards. And something like this, the Kpz equation wants to describe. And so physicists developed an equation for this, which is the following equation. So the change in time dt of h of dx equals the Laplacian of h of dx plus a non-linearity, which is the square of the derivative in space. So space is one-dimensional here, plus psi of dx. So this is the equation developed by physicists, and actually in the course of this course, we will try to understand this equation a little bit more. So what are the ingredients here? This psi of tx, that's the random term, that's what we call a space-time white noise, which I will still explain in more detail. Yeah, so that everything will be explained. So here, psi is what we call the space-time white noise. White noise. So what does this mean? So psi, first of all, is something Gaussian, it's something centered Gaussian. And so as you can see, it depends on space and on time. So if you have something Gaussian, well, in order to describe it, what you really need to do is to describe the covariance structure. And actually, this psi of tx is such that it's completely decorrelated. So if you take two different space-time points, tx as y, if they're different, well, then these two random variables, psi of tx, psi of y as y, are independent. Psi is centered Gaussian. Centered Gaussian, such that it's completely uncorrelated in space and time. So formally, we write it like this, and again, so I will explain this still. So the delta at x, evaluated y times the delta at t, evaluated at s. Yeah. So for now, simply imagine that on each point of space-time, you have an independent normal random variable. Okay? Okay, so that's the equation. And now you can try to study this equation. So maybe one challenging term here is this non-linearity. So let's have a look at it. And well, the solution is supposed to take such a form. So this is supposed to be the graph of the solution at a fixed time. Yeah. So this here really be fixed time, and then the graph of solution in space really looks like this. And so what we need to do is, in order to understand this equation better, I mean, one thing we need to do is we need to calculate the derivative in space of this guy, right? And if you look at this here, I mean, as I said already, this thing that I drew is far too smooth. The solution does not look that smooth. So if you actually zoom in at such a bit that looks super smooth, actually what you have is something like this. Yeah? So actually the derivative of this guy will not exist in any classical sense. Yeah? So actually, I mean, if you want to compute the derivative and you look at it, so yeah, then the derivative should be either plus or minus infinity, right? So either it really grows instantaneously or falls instantaneously. So that's one of the problems that we have. So problem is that the derivative actually should be formally plus or minus infinity. If you formally calculate it with the formula, you know, from graduation. So then, of course, it's not really clear what this actually means. So here we have infinity squared. So it's not really clear. It's not obvious how to give a sense to this equation. So actually, a more honest way to write this equation would be like that. More honest way to write the equation would be something like this: dt, of h of tx is a Laplacian of h of tx plus the non-linearity minus infinity plus psi of tx. Yeah? Simply because, well, we don't want to have an infinity on the right-hand side, so we need to subtract it. And wait, there were some things in the chat. Okay. Okay, so now you look at this equation, actually it's still not clear what this means. So, I mean, the question remains is what does it mean? What does that mean? Does that mean? Right? I mean, I said, okay, the more honest way would be to subtract infinity from the equation, but actually, I mean, it's still complete nonsense what was really written there. And so actually around 2013, Martin Heider gave a sense to it. And so I will still write down the result, but more or less what it says is, well, okay, so there's a problem of defining this equation. So what you could do instead is, instead of looking at the white noise directly, you look at a smooth approximation of the white noise, some psi epsilon. It then turns out, if instead of the white noise you have something smooth there, the equation makes perfect sense. So there's no need of subtracting infinity or anything crazy. The equation makes sense. And then what you could do is you can kind of take out the smoothing of the noise, really to approximate psi. And then what turns out, so what you then have is some kind of sequence of equation. And what turns out that if you want the sequence of equation to converge, you actually need to subtract a constant that goes to infinity. So let me write it down. So this was what I consider really a small revolution. Small compared to what comes afterwards. So Heider in 2013, using rough path theory, actually. So he proved more or less the following: that psi epsilon be a smooth approximation of psi, a smooth approximation of psi. Yeah. So what he proved then there exists a sequence of constants, there exists a sequence of deterministic constants, C epsilon, such that C epsilon actually tends to infinity as epsilon goes to 0. Yeah. And such that the solutions to dt h epsilon of tx, which is Laplacian h epsilon tx plus dx h epsilon tx squared minus c epsilon plus psi epsilon tx converge. To some function h, to some function h. Yeah. So that's the result. And okay, so first of all, this looks very weird. So you kind of need to justify that, well, okay, so you can accept that this result is true, but now you need to justify that actually what you did makes sense, is reasonable. And it turns out that this function h is actually the physical relevant solution. So the physicists, when they talk about the Kpz equation, they have a quite good idea of what they mean with that. And it turns out that this function h is really the object physicists talk about. So this really means that this is not just some kind of a mathematical nonsense that is happening here, but that's kind of really gives the physical object that we really want to understand. And h is the physical relevant solution. Physical relevant solution. Right. Solution. Okay. So not sure if there are already any questions. Okay. So
sorry, Dirk, I have a question. There is a way to mathematically state what is a physical relevant here?
Yeah, it's so one thing you can do is there's a so-called trick. It's a so-called Kohl-Hopf transform. If you look at the exponential of h, yeah, you can try to do this. It turns out that the exponential of h satisfies a certain equation, so-called multiplicative stochastic heat equation. Yeah? So then you can study the multiplicative stochastic heat equation. You can study its properties. If you want to go back to Kpz, of course, you need to take the log of that. And actually, there's a small problem when you take the log of it. But if you ignore this problem, you simply ignore this problem, then you arrive at what the physicists would call the relevant solution, which is so-called Kohl-Hopf solution.
Okay, thank you.
So in the state of the theorem, it will be written coincide with the Kohl-Hopf solution.
Okay, thank you.
Okay. Okay, so comments about this constant, I mean, it's deterministic as a rho. There's a precise formula for this, actually. I think it behaves like 1 over epsilon, it explodes like 1 over epsilon. The second thing that we observe also here, I mean, what is maybe not completely unnatural is that when you have an equation, you want to understand this equation, that first, instead of looking at the rough noise, you look at a smooth approximation, then you study this equation. Yeah? And naively, of course, what you will expect is that, well, actually that you would need to look at this and send epsilon to 0, and well, the limit should be the thing that you really want to understand. So you really could hope that this works. Looking at this sequence of equations, sending epsilon to 0, and declare the limits to be this solution you want to study. It's completely natural, of course, to do this. And it would be great if this would work, but however, this simply does not work. So if you only look at this sequence of equations without the C epsilon, then there's this sequence does not have a limit. So you're really forced to subtract the C epsilon from it, this kind of divergent constant. Yeah. So this kind of shows already that there's a certain problem of continuity. What do we mean with the problem of continuity? Well, again, I'm looking at this equation. Now we assume that psi epsilon converges to psi, so you could hope that h epsilon converges to some h. If this would be the case, it would simply mean that this equation that I wrote down here is a continuous function of the noise. The fact that this is not true, that when psi epsilon converges to psi, that h epsilon does not converge, shows that this equation is not a continuous function of the noise. So, in other words, really, what you need to come up with is some kind of a topology under which this equation is continuous. And this is essentially all what regularity structure is about. And some of you have been in the course of rough path, and rough path is essentially also about this, to find a topology where certain objects are continuous. If you haven't had a course about rough path, but you know what is the E2 integral or Stochastic integral, then essentially you did the same thing. So if you want to define something like this, bt dbt, right? So you can first try to make sense of it almost surely for each realization of the Brownian motion. And then unfortunately it turns out that this is not possible. So then you can try to define this object as a certain A2 limit also. So you change the topology in order to give sense to it. Essentially, we're the same we need to do here. Okay. Okay, so that's the first comment. The second comment, and this I will also write down, is, I mean, it's still kind of weird to have to subtract this thing. But if you think about it, in probability theory, this is what we do constantly. So compare renormalization. That's what is called this subtraction of this constant with a CLT, with central limit theorem. And nothing else is happening here. I mean, what does the central limit theorem say? So let's say you have IAD random variables with, say, some fixed variance, say 1 and mean 0. So what does the central limit theorem say? It says that this object here converges, right? The sum from 1 to n xi converges. Let's say different from 0. It says that this object converges. Actually, there's a renormalization here, right? I mean, because the way you can write it, you can also write it like this. Xi minus square root of n times the expectation of x1. If the expectation is not 0, this thing here really will explode. So this is the renormalization constant in the central limit theorem. Yeah. So I really just want to show that renormalization can be something normal, something standard that we do all along. Okay. Anyway, going back to this equation, so Heider did this using the theory of rough path, and which is nice, but this theory actually is restricted maybe to the one-dimensional situation. So when space is one-dimensional. And so there was a desire for theories that can also treat higher dimension as PDEs, stochastic partial differential equations. And this came shortly afterwards. So it's something that I would call maybe a big revolution. Yeah. So Gubinelli, Imken, and Perkowski. So in 2015, they came up with so-called power control distributions. I will not talk about this, but this, I think, fair to mention them, power control distributions. So there's another theory that can reproduce the result here, but it's applicable to other single stochastic PDEs. And so finally, this is what I call a huge revolution. It's the work of Heider. In 2014, 2014, about regularity structures. Okay. non-linearity structures. Okay. And well, the course will be about the letter. Okay, so now, so this was kind of a short introduction. So now let's go back to this equation. And so the plan is the following. So first of all, I did not really explain it, what is this white noise. So to be honest, when I started to work with Martin, I had no idea what is white noise. So let's first talk about what is this C, what is this white noise. Then what we will do is we look at the linear equation. So we will ignore the non-linearity for a moment. Yeah. And just afterwards, when we understand the linear equation a little bit better, we will talk about non-linear equations. Okay. So if there are no questions, I will continue. So now let's talk about white noise. Okay. So what we want to define, is this. Or we would like to use this definition. That C is the space-time white noise. Space-time white noise. If C is centered Gaussian, so C is some kind of a field, psi of Tx, T x in Rd, in R times Rd, let's say, Tx in R times Rd. If C is centered Gaussian, if C is centered Gaussian, such that the covariance of C takes the form I already mentioned. Psi of Tx times psi of Sy is a Dirac in X times a Dirac in T. Yeah? So this is the definition that we would like to use. If I write it like this, what it really implies that for each T and X fixed, psi of Tx is a random variable, right? So the problem is, it actually turns out, and we will see this also later, essentially why, is that psi is not a random function. So you can't see psi as a mapping that maps R times Rd to R. This is unfortunately not possible. We'll see a little bit later why. So this means that this definition is beautiful, but it's not rigorous, so it does not make sense. So psi is not a random function. We'll see that psi cannot be a random function. Be a random function. So this simply means that this definition we can't use, so we need to come up with something else. And the
a question. It is easy to see that we cannot find a random function with this definition.
Well, we see it a little bit later.
Okay.
Okay. You can already ask yourself already, what does this actually? I don't know. Maybe Christian has a fast way of explaining this. So what I mean with here, that's really the Dirac distribution. So the covariance is already described in terms of a Dirac distribution, so where you can ask yourself if this makes sense or not. But we will really see much later also a hint of it.
But from the correlations, we already have a hint that it must be a distribution, right?
Yeah.
Thanks.
So, I mean, what we could do is, I mean, when it's a random, so it cannot be a random function, so it must be a random distribution. So this means that actually we need to, instead of plugging in a space-time point of C, we need to plug in some function. So we can now try to see what is this action on a function? What should it be? Kind of assuming a formula for the covariance, which is basically that. So let's see. Let's do a heuristic. So let's see, say psi is smooth. Yeah. then the way to think about it, think of, and when you write something like this, psi of f, the way to think about it is really that we integrate our smooth function with respect to psi. Yeah? So what I wrote here is not formal, but that's maybe a good way to think about it. Maybe. Smooth, exactly. Yeah, maybe it's not so readable. Thanks. Yeah. F smooth, I know I see. F smooth, thanks. So if you accept this, what's then the covariance between psi of f times psi of g, where both f and g are smooth functions? Well, so let's simply copy what we have here. I mean, the way we think about it is that the first thing is the integral of the function f with respect to psi, whatever that means, times the integral of the function g with respect to psi. Right? So we have the product of the two integrals here. So this will give us a double integral, and we'll have something like f of xs, g of yt, let's say, expectation of psi of psi of dx, ds, psi of dy, dt. Something like this will obtain. If we now go back to our formula, I mean, we assume that we have something like this, right? So this essentially means that this expectation basically should be the Dirac in x of dy times the Dirac in dx, yeah, in dx, the Dirac in ds, yeah, dt, yeah? Which of course doesn't make sense, but this kind of suggests that actually the result should be this following integral. F of x times g of xs dx ds. And this is a beautiful formula because if you think about it, this is nothing else than the two scalar product between f and g. Yeah, which of course perfectly makes sense. Makes sense for smooth functions and actually makes sense for a much wider class of functions, two functions, of course. Yeah. And then you can say, well, okay, so then this makes perfect sense. That's very nice. So let's take this as the definition. Yeah? And this computation shows more or less how it is really related to the intuition we had about it. Yeah? With the advantage that it makes sense. Okay, so that's maybe a better definition, and that's the correct definition. Better definition. So again, so you can stop me if I'm too fast, I don't know. So let's see. So denote by S prime of R times RD, the space of all Schwarz distributions, Schwarz distributions, the space of all Schwarz distributions, on R times RD. So just as a reminder, so what is a Schwarz function? That's the function that is C infinity, and that at infinity decays faster than any polynomial or inverse of any polynomial. So given this, then psi is called a space-time white noise. It's called space-time white noise. Space-time white noise. White noise. if it is a random element, if it is it's a random element of S prime of R times RD. So it's not a random function, but a random Schwarz distribution. With Gaussian law, such that the expectation of psi of F times psi of G is the L2 scalar product between F and G for all functions in the Schwarz space. So this is really what the white noise regularity is. But what I mean with this is that it's a Gaussian process. So this means that the finite dimensional distributions are Gaussian, or the finite dimensional distribution. So this means that if you take, say, n functions f1, f2, f3 until fn, and then you look at the vector xi of f1, xi of f2 until xi of fn, so it's a random vector in Rn, right? And I want this random vector to have a Gaussian distribution. And does this answer the question?
And so we take any test functions, we evaluate the distribution, and we get a Gaussian vector. But what's the correlation matrix?
If you would take, so I mean, the correlation matrix, what you would need to do is take Fi and Fj, right, and compute the correlations between Fi and Fj, right? That's what you need to do to compute the covariance matrix, no?
Okay, you just need to compute the pairs.
Exactly. Yeah, exactly. You just need to compute the pairs.
Okay. Okay. Thank you.
Good to clarify this. Yeah. So yeah, for those who don't know this, so if you have a Gaussian process, or the process called Gaussian process if it's all its finite dimension distributions are Gaussian. Okay. So this is what's called a space-time white noise. So that's nice. So it's a bit more rigorous. And so you see, initially we define it as a random Schwarz distribution. Yeah. So the only functions that initially we are allowed to plug into the psi are C-infinity functions that decay faster than the inverse of every polynomial at infinity. However, what you see here, I mean, on the right-hand side with the L2 scalar product between F and G, so actually this, of course, makes not only sense for Schwarz distributions, but well, for L2 functions. So it actually turns out that you can kind of extend this psi to a random distribution on L2. Yeah. So that's an important remark. Yeah. Psi can be extended to an isometry from L2 R times RD into or to L2 of omega Fp. Right? Where omega Fp is, of course, the underlying probability space. Okay.
This underlying probability space is where we define the random, the white noise.
Exactly. Okay, so this is space-time white noise, and of course, so here when I write R times RD, I'm implicitly assuming that D is at least 1, so that the full dimension of R times RD is at least 2. But of course, you can do really the same with D equal to 0, so white noise, space white noise. So you can really do the same, and let's look at this case, even though it's formally not contained this definition, you can really repeat the same definition, replacing R times RD by R simply. So let's look what we get in this case. So remark. So if R times RD is replaced by R, so what do we get? So in this case, we can make a very special choice of our L2 functions, right? So for our L2 function f, we can take the indicator function on the interval 0t. Yeah? From the remark above, we learned that we don't necessarily need to choose a smooth function. It's sufficient if it's square integrable. Yeah? Times psi of the indicator function of the interval 0 s. Yeah? So what is this? Well, I mean, this formula here teaches us that it's really the L2 scalar product between the indicator function 0t and the indicator function of 0s. So this is really the integral, the indicator function of 0t of u, let's say, times the indicator function 0s of u, du. And so then it turns out that really the minimum between t and s. So I hope this little computation is clear. So here this is an s. So what does it teach us? I mean, so what do we know about psi? First of all, psi is Gaussian. And if I look only at these kind of functions, I mean, it has this covariance, and we know that if you have something Gaussian, the only thing you need to give or to define is the covariance, and then you have defined the whole process. And T has actually the same covariance we have for Brownian motion. So this really turns out, if you look at this as a function of T, then this is a Brownian motion. Okay, modulo the problem with the continuity of the sample parts, of course. But well. Yeah. So what follows really that if we think of this thing again as the integral from 0 to t of psi dr, so this is a Brownian motion. It's a Brownian motion. And so what does this really mean? I mean, above, we tried out our first definition. I mean, the first natural goal is really to make sense out of psi of tx evaluated as space-time point. So in the case of the one-dimensional situation, it would make sense to try to make make sense out of it at a given time point, at a given point t. Yeah. So what would this mean is that then actually psi of t should be really derivative of the Brownian motion, derivative of the Brownian motion. Yeah. That's what it really implies. And well, now you all know that actually a Brownian motion is not differentiable. So this derivative can only exist in a kind of generalized sense, in a distributional sense. So it's a very good indicator that white noise actually is not a random function. So maybe Guillermo, this explains a little or gives a partial answer to your question.
What question?
The question how to see that white noise doesn't make sense as a function, as a random function.
Because it will be the derivative.
Exactly, derivative of Brownian motion. So, yeah.
I have one question. We suppose we already defined the one-dimension white noise. So applying to this special class of functions, the indicator 0t, we get the Brownian motion. but I think we have more functions to apply.
Sure.
And this gives a richer universality class in some sense. I mean, the Brownian motion is scaling of the Rundle walk.
Mm-hmm.
These more general things can be obtained in a similar way.
Yeah, you can also obtain it as scaling limits. Yeah. I'm not sure if it gives something really richer. I mean, the way you think about it, if you have some psi of f in the one-dimensional situation, is that you would do something like this still. So this kind of suggests that these things are still kind of the building blocks.
I see. So you are integrating with respect to the derivative of Brownian motion.
Yeah,
and
exactly. That's the idea. Yeah.
Oh, thanks.
Okay. So now we hopefully know more or less what is white noise. So in the general case, white noise is a Gaussian process with a covariant structure. In the one-dimensional setting, it's really the derivative of Brownian motion. That's really what it is. And so now let's try to understand white noise a little bit better. And one thing that is very, very helpful is to understand how it behaves in the scaling. Yeah. So, you know, for instance, that if you look at Brownian motion, so Brownian motion has a certain scale invariance from which you can deduce many, many properties. For instance, this kind of scale invariance of Brownian motion can suggest that Brownian motion is only one half Hilbert continuous, so slightly less. So a similar thing you can try to do with white noise. So this is the next thing we will talk about, scaling of white noise. And well, what you would like to look at it, want to look at, to study, say for tau lambda positive, what we would like to study is this. We would like to define this. So here's the tau. Tx. I mean, this is what we really would like to do. Tau t lambda x. And now we would like to study how this behaves well under the scaling. Is there some kind of scale invariance? This is what we would like to understand. There's of course a problem here because I tried to emphasize that the white noise actually can't evaluate at fixed space time points. So what I wrote here, unfortunately, does not make sense. So you kind of need to find a replacement for that. Yeah? And since we can't scale directly the argument, and since we know that white noise accepts functions to test against, the idea is to test to rescale the function, the test function. So not possible. Hence, look at the following. So actually the correct definition will be this. So we need to apply to a function. And what we will do is we rescale the function. So it's S of tau lambda F, where F of tau lambda of F at a fixed point Tx is what? Well, it's tau to the minus 1t, lambda to the minus 1x. That's essentially what you want to do. There's still something missing. I will comment on it now. And now let's first try to understand if this is already reasonable or not. So think of tau and lambda being small. Okay? So tau and lambda being small, so and let's say t and x are out of order 1. What we really look at here is we evaluate essentially psi x time point tau and space point lambda. Okay? what happens now with this? Think of a function f that is compactly supported, say support of size 1. So if this tau to the minus 1 times t is supposed to be of order 1, this means t needs to be of order tau. So t we looked at here actually is tau. If lambda to the minus 1 times x is supposed to be of order 1, x needs to be roughly of order lambda. So the x we look at here is lambda. So it's really the same that we did here. Yeah. There's a small problem still when we define this, is that we would like to define a rescaling of function f that leaves the integral of some function f invariant. Yeah. And it turns out that if you do this, then the integral of the function does not change. Yeah. Okay. Okay, so that's really the correct rescaling that we look at. And so now let's have a look at this object. How does it relate to the original object? Yeah. So then the expectation of psi tau lambda of f squared. So what is this? So that's an integral of s tau lambda of f of tx squared dt dx. So what is this? This gives us a tau to the minus 2 times lambda to the minus 2d. Is this thing squared? Times the integral of f of tau to the minus 1t lambda to the minus 1x squared dt dx. Okay. What we now can do is we can do a change of variables. If you do a change of variables, it turns out that you kill 1 tau and that you kill lambda to the minus d. F of t x squared dt dx. Okay. So what is the last thing? The last thing is really this last integral is the L2 norm of f, or the scalar product of f with itself. I will close the window here. So the last integral is the L2 norm as the L2 scalar product with f with itself, of f with itself. So this tau to the minus 1, the lambda to the minus d, expectation of psi of f squared. In other words, what this really is the expectation of tau to the minus 1 half, lambda to the minus d half, psi of f squared. So what does this tell us? Since I could also repeat the same calculation with f and g instead of only f. This really tells us that this object here, psi tau lambda, has the same distribution as psi multiplied with tau to the minus 1 half, lambda to the minus d half. So it's the consequence. The consequence of this is that psi of tau lambda is the same object, in law at least, as tau to the minus 1 half, lambda to the minus d half, times psi. Yeah? And again, if you think of the one-dimensional case, in which case psi, the white noise, is a derivative Brownian motion, this also makes sense, right? In the one-dimensional case, the lambda would not be there. You only would have a tau, and in case of Brownian motion, it would be tau to the plus 1 half, but since you take one derivative, the plus 1 half turns into minus 1 half. Yeah? So I hope this was more or less clear.
Can you explain these heuristics again? This one last.
So
no, I mean the comparison of the one-dimensional case.
Yeah. So the one-dimensional case, so you need to think of d equal to 0. The one-dimensional case, so lambda would not be here, right? And it will result in with tau to the minus 1/2 times psi. Okay?
Okay.
Now what you can do is you can, yeah?
Because for the Brownian motion, b tau squared t has the same distribution as tau bt.
Exactly. So Brownian motion, well, let's do it, say tau t would be the same in law as tau the 1/2 times bt, right?
Yeah.
That's really what you said. I use tau, you use tau squared.
Okay.
Right?
So when you take derivatives,
you lose, well, when you take a derivative, this plus 1/2 turns to minus 1/2. You need to subtract 1 because you take one derivative.
Mm-hmm. I see. Thanks.
And you can, it's right, because when you take here the derivative forming time, because of the chain rule, you will get a additional factor tau here, which you need to bring to the other side. And this gives you tau to the minus 1.
Yeah, it's clear now. Thanks.
So great. So now we know how psi scales. And this actually already tells a little bit about the regularity of psi. We'll come back to this a little bit later. But for instance, as in the case of Brownian motion, this 1/2 really tells you that Brownian motion is almost 1/2 Hilbert continuous. This really will tell you that the psi has some kind of negative regularity. Yeah, but we will come back to this later. Okay. So this was a little bit the part about the white noise. So we'll come back to this. But now let's go back to the Kpz equation. So let's go back. Maybe go to the original equation. So that's the Kpz equation. So now we talked about psi. Yeah? So next, what I would like to do, I would like to talk about the linear equation. So for now, I will ignore this and we try to understand a little bit better the linear equation. That's what we do next. So this now scaling behavior of SPDs. So let's start, as I said, with a stochastic heat equation. Stochastic heat equation, which is dt of z Tx is equal to Laplacian of Z dx plus psi of Tx. And do I want to show the computations? Maybe not. Maybe not. So what is this? What you can, maybe it's good to see these computations. Scaling. So as for the white noise, what you can try to do is we can try to define a rescaled version of this equation, which is lambda to the alpha times z of lambda to the beta times t times lambda to the gamma of x. And now you can ask yourself, well, how to choose alpha, beta, gamma such that at least in law the equation does not change. So under which scaling is this equation scale invariant? I mean, this teaches us already a lot about this equation. So what we need to do for this is we need to try to derive an equation for the z hat, and afterwards adjust alpha, beta, gamma such that the equation of z hat coincides at least in law with the equation of z. So let's try to do this computation. It's maybe good to see the complete computation. So then the derivative of z hat in time. So what will we obtain? Well, we will have a lambda to the alpha here, right? This guy. And if we take of this guy, the derivative in time, we gain an additional lambda to the beta by the chain rule. Ez evaluated at lambda to the beta t times lambda to the gamma x. Okay. Lambda to the alpha plus beta. Now dtz we know satisfies this equation. So it's Laplacian of z evaluated at lambda to the beta times t, lambda to the gamma times x, plus, okay, here will be a bit informal, psi evaluated lambda to the beta t, lambda to the gamma x. Okay, nice. So what we would like now to have here, we would like to have an equation for z hat. So instead of the Laplacian of z, we would like to have an Laplacian of z hat. So how does it scale now? So Laplacian of z hat, that's what we really would like to have here. So let's see. So again, we will have a lambda to the alpha here, right? It's this factor. And we take two derivatives in space. So the chain rule tells us that we will have a 2 gamma here. Laplacian of z of lambda to the beta t, lambda to the gamma x. Okay, nice. And another thing is here we have the white noise. Fortunately for the white noise, we already know how it scales. So psi of lambda to the beta t, lambda to the gamma x, at least in law, it coincides with lambda to the minus beta over 2, lambda to the minus gamma over 2, times t, sorry, times psi tx. Yeah, that's this exercise that we just did. So what we can do now is, so the first thing here gives us an equation for Laplacian of z, right? The Laplacian of z that we have here, which tells us that the Laplacian of z is simply lambda to the minus alpha minus 2 gamma times the Laplacian of z hat. So we can plug this into the above equation, which tells us that dtz hat of tx is lambda to the alpha plus beta. Now I would like to have the Laplacian of z. Laplacian of z is lambda to the minus alpha minus 2 gamma. Laplacian of z hat. Yeah. And for psi, I will plug in this. Lambda to the minus beta half, lambda to the minus gamma e half. So plus lambda to the alpha plus beta, lambda to the lambda to the minus e half, beta half, lambda to the minus gamma delta half times psi of tx. Okay. So that's the equation that you obtain. And now what you would like to do is you would like to determine alpha, beta, gamma such that this equation is scale invariant for these values of alpha, beta, gamma. So in other words, all you need to do, you need to determine alpha, beta, gamma such that this becomes 0 and such that this becomes also 0. Yeah? And one possible choice is the following. Yeah? So we can choose alpha to be d half minus 1, beta to be equal to 2, and gamma equal to 1. And at this scaling, the z hat has the same law as z. So you can shortly check that this is correct. Yeah? So here alpha and alpha cancel. Here you get the condition that beta must be equal to 2 gamma. Yeah. So this is fulfilled with this choice. Yeah. And okay, so that this is 0 if you choose alpha in this way. Well, that's something you can try to check. Okay. Here, are there any questions? the same law as that. Okay. Okay. So in case
I have a question.
Sure, go ahead.
In the Minicurso, are we going to prove the existence of the white noise and the solution of the stochastic equation, or you are going to assume?
No, we will assume it.
Okay.
So, yeah, so otherwise it would be hard to go to really regularity structures. But I guess there are
leave it as exercise
on about the stochastic differential equations, probably show construction of the white noise. So you can construct white noise, for instance, Fourier space. There are several ways of showing it. So that
Dirk,
expression. Yeah.
So maybe I just didn't get it, but did you assume something about the initial condition of the equation?
No, nothing. So I think probably one, I guess.
Okay. Okay. So when you say that the C tilde is equal in law to Z, that you probably mean that the invariant, the starting, the initial conditions is also invariant, no?
Yeah, exactly. So maybe it's a good comment. So here in this course, I will always assume that the initial condition of everything will be smooth and that there are no problems with the initial condition. So simply to simplify a little bit what we will do. Of course, there are also directions, also in the theory of regularity structures, where one tries to generalize the initial condition one chooses, but this gives some extra amount of work. So here in this course, I will essentially ignore the problems, possible problems coming from the initial condition. Okay, so nice. So this now tells us how we need to scale the stochastic heat equation so that it's scale invariant. And now, so let's go back to Kpz just to see this equation again. So, I mean, what is Kpz? So now if you, and here we are. So now if you look at Kpz essentially is something like the stochastic heat equation, right? Plus this nonlinear term. This is also something that we will still do. So I think probably next class we will talk about the regularity of the stochastic heat equation. But I can already tell you now is that essentially the solution to the stochastic heat equation has two more regularity than the white noise. Yeah, exactly.
And the regularity of the, we are going to prove also the regularity of the white noise?
Yes, exactly.
Okay.
Exactly. So the regular, okay. I will still come to this. But I think when you're right, is I think 1/4 in time and 1/2 in space. Yeah. Okay, so if you look at this Kpz equation again, it's essentially a stochastic heat equation plus a nonlinear term. And so now one thing that you could try to do is say, well, okay, so now we know under which scaling the stochastic heat equation is scale invariant. What happens if we take the same scaling for the Kpz equation? Does it teach us something? Yeah. So this is kind of a very cheap way of kind of getting a feeling how the Kpz equation behaves compared to the linear equation. Yeah. It's of course maybe informal because we don't know if solutions exist, but let's assume solutions exist, and let us see how they behave in relation to the linear equation. So this time I will not do all the computations, but let's go back to Kpz. Yeah. So let me write it down again for those who don't know. This equation is dth of dx. So now I really write what it is. So in the one-dimensional setting for the Laplacian the second derivative, dx h of tx squared plus psi of tx. So if d is equal to 1, then actually what you have is that alpha is d half minus 1, so alpha becomes minus 1 half, right? Beta stays equal to 2, does not depend on dimension, and gamma is 1. So then, if we define h hat of tx the same way, lambda to the alpha, so lambda to the minus 1 half, times h of lambda to the beta, so this lambda squared, times t, lambda x. So then, if you do the same computations as above, you can now check what kind of equation this satisfies. And so, at least in law, what you find is that, well, let's write the second derivative. The second derivative h of tx, psi of tx. So here with the linear part, there's no surprise, of course, that the linear part stays untouched because, well, we choose this experiment in such a way that the linear part doesn't change. But we will see that the linear part actually changes. It's lambda to the 1 half times dx h hat of tx squared. So that's a computation that you need to do. It's probably not visible immediately, but that's a computation that you can do. And now, so what does this mean? So let's assume lambda is small. So let's assume that we can send lambda to 0. When we send lambda to 0, what will happen? Well, here with lambda squared times t, here with lambda times x. If lambda is very, very small, actually here we look at space-time points close to the origin, right? Actually, we look at a small-scale behavior. And what turns out, when lambda goes to 0, this non-linearity has a factor in front that vanishes. So this means that at least for very small lambda, the non-linearity should not matter too much because it formally vanishes. And actually, every time this is the case, you have a certain equation. You extract the linear part, you check under which scaling is this linear part invariant in row at least. You use the same scaling for your nonlinear equation. And if then the nonlinear equation vanishes formally at least, as lambda goes to 0, then you call this equation subcritical. And this is exactly the regime when you can use regularity structures. So we come to one of the central definitions of the theory of regularity structures. So consider the equation. Let's say dtu is Laplacian of u plus some nonlinearity which may depend on u, perhaps the gradient of u, as in the case of Kpz, plus psi. This equation is called subcritical, if under the above scaling, the nonlinear term f of u, Laplacian of u, formally gets transformed. Formally gets transformed . into a term, f lambda, u gradient of u, which formally goes to 0 as lambda tends to 0, which formally goes to 0. Goes to 0. Oops. Goes to 0 as lambda tends to 0. Yeah.
Is this a precise definition?
Not completely precise. So in the original paper, the definition is a little bit more involved. But in the Gaussian situation, it's really that. I think it's essentially rigorous. But it's not the definition that you find in the original work.
Okay, thank you.
So why don't you find this in the original work? So this thing here is, in order to determine the scaling under which the linear part is invariant, I used, of course, also the Gaussian scaling, right? The scaling from the psi. Regularity structures also work when psi is not Gaussian. Yeah? So when there's no clear scale invariance or so, you can still.
But for Gaussian, for the white noise, this is very precise.
Yeah, exactly. You could also imagine to replace this Laplacian by some other linear operator. Then you would need to change the scaling of the linear equation, but then the definition goes still through. Yeah. All it says really that as lambda goes to 0, you really need to think of looking at the equation in small scales, that the non-linearity is only a perturbation. This is a subcritical regime, and it is exactly this regime in which you can apply the theory of regularity structures. Maybe just one comment.
Just one question. Why we don't care for large scales when lambda is big?
We do also care a lot, but regularity structures is a local solution theory, so it really only can look at small scales.
I see. We just want to prove the existence of a local solution near. Exactly.
And essentially, it always works when the non-linearity is with a perturbation of the linear equation. We will see this much later also under the point of view of regularity, right? I mean, the theory is called regularity structures, and now we did not talk about regularities. This will still come. Of course, we also care about large scales. For instance, you may be interested in the case where lambda really goes to infinity, and then what you really see here is the non-linearity blows actually up. And at large scales, when you should observe what is called the Kpz fixed point, but it turns out that scaling is different. Yeah. And so every time the equation is subcritical, so if as lambda goes to 0, the non-linearity formally vanishes, the theory of regularity structures applies. You can now ask yourself, well, let's take the Kpz equation higher dimensions. In higher dimensions, you can do the same computations. Yeah? So we have this general formula for alpha, it's d½ minus 1. And then it turns out that in dimension 2, if you take the same scaling, the exponent would be 0. Yeah? So there would be no lambda. And dimension 3 and higher, actually, you would divide by lambda. So dimension 3 and higher, when you set lambda to 0, the non-linearity formally goes up. This is a so-called supercritical regime. Yeah? So on small scales, the non-linearity is dominating. In dimension 2 is a so-called critical regime where it's actually not really clear.
But regularity structures also only applies to the subcritical case.
Exactly. Yeah.
So we are restricted to dimension 1 for the Kpz.
For the Kpz equation, yes. There are other equations where you're not restricted to dimension 1. But you don't need to see this as really a restriction of the theory. Of course, it's a restriction. But all this scaling argument really tells you that dimension 2 and 3, okay, I didn't do the computation, but the behavior of the equation should be really different. Yeah? Because I mean, scale invariance is something extremely important. I mean, this it's not just a nice fact, but it really provides a lot of properties. And so kind of the fact that, for instance, dimension 2, this equation will be scaled in, might really show that it's really a different class of equations. So in a certain sense, this theory is really optimal. Okay. So now let me say kind of the last result of this class, which I will not prove, but which really tells you what I just said. This is so-called meta theorem. So it's not a formally complete theorem, but it kind of tells you more or less what regularity structures can do. So let's call this equation star. Star. So assume that the SPDE, star is subcritical. Is subcritical. Yeah. So assume that space is compact with nice boundary conditions. Compact with nice boundary conditions. So there's something I, for now, really want to ignore. Boundary conditions. And let the initial condition U0 be smooth. Condition U0 be smooth. Yeah. So then there's a natural, there is a natural notion of solution. Notion of solutions to star. So such solutions exist such solutions exist and are unique on a finite time interval. A finite time interval. Interval 0t for some random t or some random t positive. So essentially this theorem this kind of summarizes all the results that there are in the theory of regularity structures. Of course, some of them you can really relax. For instance, that space is compact. So in some cases, we know that we have also global space solutions. So these are the more questions that really depend on the precise equation at hand. Yeah? But as long as you have nice boundary conditions in space, compact space, sufficiently nice and smooth initial condition, the only thing you really need to know about the SPD that's subcritical. And the theory really goes through. Okay. So I think I will stop here. Maybe I'll just give one thing as an exercise. There are no questions. So need for renormalization. Normalizations. So if you look, no, I will do it next time. So, okay, I think I will stop here. Are there any questions, comments?
Any questions? Sorry, in English or Portuguese?
Ah, sim, 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 pode ser português também.
we will have exercise lists.
No, but okay. So if you want to do one exercise, so I was hesitating showing this computation, but since you're asking, so if you look at that's maybe a good exercise to do. It's a bit cumbersome to do the computations, but it's elementary. So if you look at the PAM equation, yeah, and you look at, so I didn't prepare any exercises. And you look at an approximation of the white noise. So if some function, I don't know, rho delta dot delta to the minus d rho delta to the minus 1 dot will smooth integral of rho 1 rho smooth. So maybe what you can try to show using the final Kpz formula say u delta should be something like this into u delta of x. The expectation of a Brownian motion started in x exponential equals 0 to t psi delta bs that the expectation explodes. As delta goes to 0. So here I forgot, so C is your space white noise. So if you want, you can think about this. I hope this was not too fast. So what we really do is we look at the PAM equation. We smoothen out the white noise with some kind of smooth modifier that integrates to 1. And then you can ask yourself if I define the equation u delta like this, if you convert this, delta goes to 0. And since here we have a precise expression for the solution, you can actually convince yourself that this is not the case. So there is really a need for a linearization here, that there's no chance that this thing simply converges. This may be a good thing to see.
And to deal with this equation, we also need regularity structures.
Yeah, exactly. In dimension 2 and 3. So what you will see is in dimension 1, there's no problem. So, and in high dimension, yes. Yeah. Okay. So, okay. So you can have fun with this.
Thanks.
Okay. Are there more questions?
A simple question. Then, in order to apply the regular structure, you need the regularity of the path distribution plus the scaling of the distributions.
The scaling?
You need two information, regularity and the scaling.
Actually, the only thing that you really need is the regularity. But in many cases, you can guess the regularity from the scaling. So that's why the scaling is still very helpful. Okay. So actually, next class, we will derive the regularity of white noise. And do this, this will be a consequence of the scaling.
Okay.
So regularity of white noise and hopefully regularity of the stochastic heat equation. This is so essentially everything depends on regularities. Okay.
Okay. Another questions? Comments?
So I have a question, a quick question. Maybe it's too technical. Maybe or maybe it's a little bit stupid. But so I don't know if you know the parametrics method to solve parabolic equations, and I wonder if you're if there is a relation between regularity structures and these parametrics methods in parabolic equations.
I don't know, so I don't know this method. So just a quick answer, I guess. I don't know this method, so I don't really know.
Okay.
Okay, we continue on Wednesday, 4 o'clock. The link is in the web page, which is in the chat. Okay. Bye-bye, thank you.